Hello everyone. So, in last lecture we have derived the Paul-Hausen equation starting from the energy equation. Today we will find the different heat transfer parameters like heat flux, heat transfer coefficient, Nusselt number from the solution of Paul-Hausen equation. So, you can see that dimensionless temperature we have derived in last class. Temperature for uniform wall temperature condition, that means Tw is constant, theta which is your dimensionless temperature, which is function of eta, and Prandtl number is equal to 0 to eta f double prime to the power Prandtl number d eta divided by 0 to infinity f double prime to the power Prandtl number d eta, and the derivative of theta we have also derived, and at eta is equal to 0 the expression is theta prime 0 is equal to d theta by d eta at eta is equal to 0, that we have already derived this expression a double prime at eta is equal to 0 to the power Prandtl number divided by 0 to infinity f double prime to the power Prandtl number d eta. So, once you know the temperature distribution from the Paul-Hausen solution, then you will be able to calculate the local heat flux as well as local heat transfer coefficient and local Nusselt number. And you need the value of d theta by d eta at eta is equal to 0, that means the temperature gradient at the wall to find the heat flux. So, first let us find what is the local heat flux. So, you know by definition q double prime w is equal to minus k del t by del y at y is equal to 0. So, at this wall the temperature gradient del t by del y, and that is coming from Fourier's law of heat conduction, and we have taken the dimensionless temperature such a way that T is equal to T w plus T infinity minus T w into theta, okay. And the similarity variable eta is y root u infinity by nu x. So, now you can see that this we can write minus k del t by del y. So, T w is constant in this case. So, you can write T infinity minus T w del theta by del y at y is equal to 0. So, minus k T infinity minus T w. Now, you write d theta by d eta, right, at eta is equal to 0 and del eta by del y, okay. So, del eta by del y you can see it is root u infinity by nu x. So, you can write minus k T infinity minus T w, and del eta by del y is root u infinity by nu x, and it is theta prime at eta is equal to 0, okay. So, this you can write, this minus you can take it inside. So, you can write k T w minus T infinity root u infinity by nu x theta prime 0, okay. So, we have found the local heat flux. Now, we will calculate the local heat transfer coefficient, okay. So, local heat transfer coefficient you know from the equation from Newton's law of cooling you will be able to calculate. So, local heat transfer coefficient H x you can write q double prime w divided by T w minus T infinity, and this we are writing from the Newton's law of cooling, okay. So, q double prime w just we have calculated. So, this is your k T w minus T infinity root u infinity by nu x theta prime 0 divided by T w minus T infinity. Okay. So, this you can cancel. So, you will get, we will just write k by x and we will multiply in the numerator x and we will take inside this root. So, it will be x square. So, you will get root u infinity x divided by nu theta prime 0. What is u infinity x by nu? So, you know the Reynolds number definition, right. So, this will be local Reynolds number at any location x. So, local Reynolds number okay, R E x you can write u infinity x by nu. So, this now you can write k by x okay, root R E x theta prime 0. Okay. Now, once you know the local heat transfer coefficient, you can calculate the local Nusselt number, because you know the definition of local heat transfer as H x x by k. So, local Nusselt number is definition by H x x by k. So, you can see this x by k, if you take this side. So, this will be left with root R E x theta prime 0. So, once you can find the derivative theta prime at eta is equal to 0, then you will be able to find the value of local heat transfer coefficient and local Nusselt number. Now, let us calculate the total heat transfer from the plate of length L, and we will calculate it per unit width. So, total heat transfer rate from a plate of length L, you can calculate Q W. Okay. So, just local heat flux you have calculated into area. So, per unit width. So, it will be 1 into dx okay, and that you need to integrate 0 to L. L is the length of the plate. Okay. L is the length of the plate. Okay. So, if you put the expression of q double prime w here, so the constant you can take it outside the integral. So, it will be T w minus T infinity root u infinity by nu theta prime 0 integral 0 to L dx by root x. Okay. So, if you integrate it, you will get twice k T w minus T infinity okay, and if you put the limit L, then you will get root L in the numerator. So, that will take here root u infinity L by nu theta prime 0. Okay. So, from here you can see twice k T w minus T infinity, and what it is? It is Reynolds number, right, u infinity L by nu. So, based on the plate length. So, root R E L theta prime 0. Once you know the total heat transfer rate, you will be able to calculate the average heat transfer coefficient. So, average heat transfer coefficient we will calculate H bar as Q w divided by T w minus T infinity into area, right. This is Newton's law of cooling. Okay. So, per unit width, so 1 into L. So, if you put the value, so you will get twice k T w minus T infinity root R E L theta prime 0 divided by T w minus T infinity into L. So, this you cancel. So, you will get H bar as twice k by L root R E L theta prime 0. Okay. From here average Nusselt number you calculate. So, average Nusselt number will be just H bar into L by k. Okay. So, from this expression you can see it will be twice root R E L theta prime 0. So, all these expression we have written in terms of theta prime 0. So, theta prime 0 is still unknown because you need to find it from the temperature distribution. Here you notice the local heat transfer coefficient and average heat transfer coefficient. So, you can see that your average heat transfer coefficient is double of the local heat transfer coefficient at x equal to L, and similarly average heat transfer coefficient is twice of the local Nusselt number at x equal to L. So, if you see, let us say this is the Nusselt number distribution, okay, with length L. Okay, so, this is the plate length L. Okay. So, how it varies? So, let us say your local Nusselt number varies like this. So, if this is the local Nusselt number variation, okay, then your average Nusselt number will be twice at x equal to L. So, this will be the average Nusselt number, okay, it is average Nusselt number, and you can see its value is double of this. Okay. So, what is this value? So, this is your Nusselt number x at x equal to L, and this average Nusselt number will be 2 Nusselt number x at x equal to L. So, this is your double. So, this is the same distance. So, it will be the same value. So, obviously, it will be the average Nusselt number will be the double of the Nusselt number at x equal to L. So, in this slide we are showing the temperature gradient at eta is equal to 0 for different Prandtl number. So, this has been evaluated numerically for a range of Prandtl numbers by Paulhaussen. Okay. These are the numerical solutions, and d2f by d eta square at eta is equal to 0 already we have found from the Blasius solution. And if you see the temperature distribution theta, which is T minus Tw divided by T infinity minus Tw versus eta. Okay. So, obviously, at different x location all the temperature profile falls in the same curve, but it varies for different Prandtl number. So, you can see Prandtl number is equal to 1. Okay. So, this is the case where Prandtl number is equal to 1. So, in this profile, temperature profile will be same as the velocity profile, that we have already discussed, and for other Prandtl number you can see how it varies with eta. Okay. So, at different Prandtl numbers. So, now whatever results we have shown, Paulhaussen results now can be approximated by, for different Prandtl number, this is the numerical value of temperature gradient at eta is equal to 0. Okay. So, this actually is approximated by Paulhaussen as 0.332 Prandtl number to the power 1 by 3. So, you can see if you see 0.6. So, if you put 0.6 Prandtl number, okay, here, so 0.6 to the power 1 by 3 into 0.332. So, you will get 0.280, and for different Prandtl number you can see that almost this is comparable. So, this is the numerical solution and this is approximate, okay, 0.332 Prandtl number to the power 1 by 3. So, 0.6 to 15 we have shown here, and in this range, so theta prime 0 can be approximated as 0.332 Prandtl number to the power 1 by 3. So, you can approximate the first derivative of dimensionless temperature at eta is equal to 0 as 0.564 Prandtl number to the power half. For other range I am writing where Prandtl number tends to 0. Okay. Generally it will be valid in the range of 0.005 less than Prandtl number less than 0.05. Then in this range 0.6 to 15, this is the approximation. So, 0.332 Prandtl number to the power 1 by 3 in the range of 0.6 and 15, and it will be 0.339 Prandtl number to the power 1 by 3 for high Prandtl number. Okay. So, generally it is Prandtl number greater than 15. Okay. So, now you got some approximate value of theta prime 0 in terms of Prandtl number. Okay. So, from the Paul-Housen numerical solutions, that is approximated in the power of Prandtl number. So, for the range 0.6 and 15, you can write q double prime w, because we have already found the expression. So, if you put the value of theta double prime 0 as 0.332 Prandtl number to the power 1 by 3. So, you can write as 0.332 k t w minus t infinity Prandtl number to the power 1 by 3 root u infinity by nu x. Okay. Local heat transfer coefficient, you can write 0.332 k by x Prandtl number to the power 1 by 3 R e x to the power. So, local Nusselt number you can write 0.332 Prandtl number to the power 1 by 3 R e x to the power half, and average heat transfer coefficient, it will be twice of H x at x equal to L. So, it will be 0.664 k by L Prandtl number to the power 1 by 3 R e L to the power half, and average Nusselt number will be 0.664 Prandtl number to the power 1 by 3 R e L to the power half. You can see that already we have seen the scale of this Nusselt number and the heat transfer coefficient using the scale analysis. So, if you recall, using scale analysis, we have written for high Prandtl number fluids, okay, high Prandtl number fluids, that means your thermal boundary layer thickness will be less than hydrodynamic boundary layer thickness, and generally oils have large Prandtl number, okay, of the order of 1000. Okay. So, here if you recall, we have written Nusselt number x order of Prandtl number to the power 1 by 3 R e x to the power half. So, you can see here, okay, same order with a value 0.332. Okay. Similarly, for low Prandtl number fluids, okay, delta T is greater than delta, generally liquid metals have small Prandtl number, okay, of the order of 0.01. So, if you recall, we have found Nusselt number x order of Prandtl number to the power half R e x to the power half. So, you can see the power of Prandtl number for high Prandtl number fluids, the power is 1 by 3, and low Prandtl number fluids, the power of Prandtl number is half. So, that we have already found from the scale analysis, and from this numerical solution you can see that for low Prandtl number fluids, Prandtl number tends to 0, your theta prime 0 is 0.564 Prandtl number to the power half. So, if you write the local Nusselt number for low Prandtl number fluids, then Nusselt number x you can write as 0.564 Prandtl number to the power half R e x to the power half. Okay. Now, we will discuss about the fluid friction and heat transfer relation. So, you can see that we have found the local Nusselt number as 0.332 Prandtl number to the power 1 by 3 R e x to the power half in the range of Prandtl number 0.6 and 15. Okay. Now, this we can rewrite as, which can be rewritten as Nusselt number x divided by Prandtl number into Rex. So, if you divide it, and you will get in the right hand side as 0.332 Prandtl number to the power minus 2 by 3 Rex to the power minus half. Okay. So, you can see left hand side is the dimensionless group, right. So, this is called local Stanton number. So, the left hand side it is Stanton number, okay, local Stanton number. So, this is your Nusselt number x by Prandtl number Rex. So, this is known as local Stanton number. Okay. So, from this relation you can see that Nusselt number x is hx x by k, Prandtl number is nu by alpha. So, you can write alpha as k by rho Cp, okay, and 1 by nu, okay, and Reynolds number. So, u infinity x by nu. So, from here you can rearrange it. So, you can write it as hx by rho Cp u infinity. Okay. So, you can see the local Stanton number is given by this relation hx by rho Cp u infinity. So, now you can write Stanton number x is equal to 0.332 from this expression, Prandtl number to the power minus 2 by 3 Rex to the power minus half, or you can write Stanton number x Prandtl number to the power 2 by 3 is equal to 0.332 Rex to the power minus half. From the Blasius solution we have found the local skin friction coefficient. Okay. So, if you write down the expression for local skin friction coefficient, which is known as friction coefficient, because for flow over flat plate the friction is the dominant drag due to shear stress. So, you can write Cfx as 0.664 by Rex to the power half. Okay. So, you can see from this expression and this expression you can write Stanton number x Prandtl number to the power 2 by 3 as Cfx by 2. Okay. So, this relation is known as Coleman analogy. So, this relation is known as Coleman analogy. Okay. So, this is between the fluid friction and heat transfer for laminar flow on a flat plate. You can write this expression. So, what is the advantage of using this analogy? Because if you know the friction coefficient, then you will be able to calculate the heat transfer, right, from this expression. Now, when Prandtl number is equal to 1, okay, so this expression will become Stanton number x is equal to Cfx by 2, okay, and this expression is known as Reynolds analogy. Reynolds analogy. Okay. So, you can see you can calculate local heat transfer coefficient when local friction coefficient is known on a flat plate under the conditions in which no heat transfer is involved. So, now let us consider the variable wall temperature what we started during the derivation, and we have shown from the analysis that T w varies as T w is equal to T infinity plus C x to the power lambda, where C is the constant. So, you can see variable wall temperature T w x minus T infinity you can write as C x to the power lambda, and this is the Paul-Hausen equation, right. So, this is the ordinary differential equation. So, for a special case we put lambda is equal to 0, where wall temperature become constant. So, we drop this term. So, from this equation if you numerically solve, then if you can calculate the non-dimensional temperature derivative at eta is equal to 0, that means at the wall for different value of lambda, then for different Prandtl number this is the variation. Okay. So, you can see this is the dimensionless temperature gradient variation at the wall, okay, for different value of lambda and at different Prandtl number. Okay. So, you know that lambda is equal to 0, this denotes for flow over flat plate with uniform wall temperature case. Okay. So, by numerical techniques if you can solve, then you can plot this, and once you know this value, then same expression for local heat transfer coefficient, average heat transfer coefficient, local Nusselt number and average Nusselt number you will be able to calculate. Now, when you consider variable wall temperature, then can you find the value of lambda for which the wall will be maintained at constant heat flux condition. Okay. So, this is your variable wall temperature, okay. T w is function of x. Now, what will be the value of lambda for which wall will be maintained at uniform heat flux condition. So, we have to find what is the value of lambda. So, the heat flux, local heat flux you can write as K T w minus T infinity into root u infinity by nu x into theta prime 0. So, this expression just in previous slide we have derived. Now, you can see T w minus T infinity. So, here T w is function of x. So, T w minus T infinity you can put C x to the power lambda. So, you can put C x to the power lambda K u infinity by nu x theta prime 0. So, now you can write it as K C root u infinity by nu theta prime 0 and x to the power lambda minus half, because here in the denominator you have x to the power half. So, here x to the power lambda. So, x to the power lambda minus half. So, this is the expression for local heat flux, right. So, now to maintain at uniform wall heat flux condition, it should be independent of x, right. Then only the wall will be maintained at constant heat flux condition. So, you can see here K is the thermal conductivity, that is constant, C is the integration constant, u infinity free stream velocity is constant, this is your fluid kinematic viscosity, that is also constant, theta prime 0 which is your temperature gradient at eta is equal to 0. So, that is having some numerical value. So, that is also constant, but it varies with x to the power lambda minus half. So, this term should be 1, right, then only it will be independent of x. When it will be 1, when lambda minus half will be 0. So, that means lambda minus half will be 0, then it will be x to the power 0, that means 1. So, it will become independent of x. So, lambda is equal to half. So, for lambda is equal to half, what will be q double prime w? So, you can see this will be 1. So, it will be k c u infinity by nu theta prime 0, which is constant. Okay. So, for the constant heat flux along the wall, the expression should be independent of x. So, lambda will be half. So, in today's class we have found the local heat transfer coefficient, average heat transfer coefficient, local Nusselt number, average Nusselt number in terms of temperature gradient at eta is equal to 0. Then later we have shown the numerical solution of Paul-Housen equation, and there we have tabulated the value of theta prime 0 for different Prandtl number. Then Paul-Housen approximated this temperature gradient at the wall with Prandtl number relation, and we have shown that for the range of Prandtl number between 0.6 and 15, the Nusselt number varies with Prandtl number to the power 1 by 3 and Reynolds number to the power half. The same we have shown earlier from the scale analysis as well. Later we have defined the Stanton number, and from there we have shown the Colburn analogy as well as the Reynolds analogy. So, this can be used to find the heat transfer coefficient if you know the friction coefficient. Then for variable temperature boundary condition, we have shown the numerical solution, and later we have found the value of lambda for which your flat plate wall will be maintained at uniform wall heat flux condition, and the value of lambda is